Okay. Thank you, and thanks for everyone to coming. So yeah, today I'm going to be talking about hyperbolic groups with k-geodetic Cayley graph, and possibly talking about what type of groups these what type of groups we have this k-geodetic Cayley graph property. And so this is joint work with Murray Elder, my postdoc supervisor, and Adam Piggott at ANU. So just as an overview, I'm going to introduce what a geodetic graph is. So our graph is going to be a locally finite simple connected graph. So nothing too strange going on there. And we're going to say gamma is geodetic if there is a unique geodesic between any two vertices. So to give some examples and a non-example, so any sort of tree will be geodetic, any sort of complete graph, so there's K4, that will also be geodetic since there's a unique path of length 1 to any vertice from another one. And then, of course, the even cycles will not be geodetic because you've got a path from there to there that's length 2 and a path from there to there that's length 2. They're both geodesics, and so there's not unique. So this is a sort of classical problem in finite graph theory, is to characterize all finite geodetic graphs. And it was a question posed by Orr in 1962. And so I've written down some examples here. So we've got the trees, complete graphs, odd cycles, and then there's like ways to join them up. So you get things like barbell graphs and things like that. And if you look up geodetic graphs on Wolfram Alpha, they give you examples up to 5 vertices. And my supervisor and his summer school student, they actually wrote a program and classified how many geodetic graphs there are for a given number of vertices up to, I think this is number 11. So 11 vertices. You just have to count how many numbers there are up there. I think their contribution was maybe just like this one or an extra one here. But an actual classification of these geodetic graphs is quite far off, and it seems like a fairly active sort of area of maths, but more in the sort of computer science realm. So we're going to generalize this definition of geodetic with k-geodetic. So gamma is k-geodetic if there's some k such that there's at most k geodesics between any two vertices. And we're going to apply this to the Cayley graphs of groups. So we're going to let G be a group with finite inverse closed generating set S. And this will give us our sort of connected locally finite graph that we want. But this graph could be infinite if the group's infinite. So, and we'll say that the group is k-geodetic with respect to some generating set if that Cayley graph of that group is k-geodetic. So some examples, and what we'll see is it actually does depend on the generating set we choose. So if we just take the cyclic group of order 4, and we choose 2 different generating sets. So the first one here is just all elements other than the identity. And then this one's just one element and its inverse. Then what we find is S1 will give us a 1 geodetic Cayley graph, but S2 will give us a 2 geodetic Cayley graph. So in finite groups, this is not so interesting because you can always give all the generators other than the identity, and that will give you the complete graph. But when we get to some infinite groups, then this question becomes a little bit more interesting. So to start off, though, I'm going to sort of go through a fact that in k-geodetic graphs, ladders of a particular thickness have to have a bounded length. And by ladder, I mean if we have two disjoint geodesics, then a distance m larger than 0 from each other, then we can only have it happen a finite number of times. So for a contradiction, suppose that we have it happen arbitrarily many times, then we have some sort of diagram like this. So we've got our top row, we've got a long geodesic here, and we've got our bottom row along geodesic here. And then at some points along this, they're distance m away from each other. And what I'm going to propose is, since the graph is, we're assuming that the graph is k-geodetic, there's going to exist a path from x0 to yk that doesn't go via xk, that has either this length or this length. And so maybe if I let k equal 2, then we can sort of highlight this idea. So if k equals 2, then we can travel from x0 to y0 and then along this to y2. And this is going to give us a path of length m plus d1 plus d2. And then similarly, we can go along here, or we can go along here. So that gives us 3 paths of the same length. So we know that none of those paths can be the geodesic. And so that means that there must be a shorter path. And in particular, we can deduce that it's actually 1 or 2 less. And the argument for that will be if you travel from x0 to y2 by looking at the geodesics from x0 to say 1 step along here, 2 steps along here, 3 steps along here, and so on. At one point, there's going to be a geodesic that is either 1 or 2 less. And the reason you can't get a greater number less is because then the path from x0 to say this point and then back 1 step would give you a shorter path than what you'd supposed was a geodesic. So hopefully I explained that okay. And so all that does is tell us that from x0 to say y2, there's a path of shorter length. And so what we have to do is repeat this idea. So we could do the same idea for x2 to y4 and so on. And then if you do that enough times and then repeat and use the pigeonhole principle, then eventually what you get is for some r, there's a path x0 to yr and then up to xr. And if you've done it enough times, then you're going to get a shorter distance than the sum of the d's. And so that gives you a contradiction because you've assumed that the top row is a geodesic. And so the corollary from this is that there is a bounded number of times that geodesics can be greater than 0 and less than some m apart. So that corollary just follows again by the pigeonhole principle. If you're bounded between 0 and m, then one of the distance has to appear arbitrarily many times, and so then you get a contradiction. Okay, so that's a purely k-geodetic graph argument. So we haven't looked at groups yet. So I want to focus in on some classes of groups. So the first class is a pretty simple one. They're called the plane groups, and they're isomorphic to finitely many free products of finite groups and infinite cyclic groups. And so I've given an example here with presentation. Then within these, a bigger class of groups is the virtually free groups. And so these groups have a free subgroup of finite index. And I've given another example there. And then an even bigger class of groups that we have are the hyperbolic groups. And they have a Cayley graph that is a hyperbolic space. And so to highlight the sort of containment of these classes of groups, you have the finite ones inside the plane groups, and then inside the virtually free, and then the hyperbolics containing all of them. So just to clarify what I meant by hyperbolic space, that means that the triangles, the geodesic triangles in that space are slim or thin. They're both equivalent definitions. So a slim triangle means that the distance from any point on any side is less than delta to some point on another side. So that's the more standard definition of hyperbolic space. But there's the thin triangle. So this means delta slim. And then the less standard sort of definition is epsilon thin. And so what you do is you take your geodesic triangle and you can construct these points on these sides so that this side length is equal to this one, this side length is equal to this one, this side length is equal to this one. And what it says is the distance as you travel synchronously along from here to here is less than epsilon always. So the distance from here to here, here to here, here to here, and so on. So you can sort of see that maybe we're going to have some sort of ladder structure going on here. And I thought I would start with a pretty sort of diagram to, I don't know, show you that there are some at least interesting examples of geodetic graphs that are infinite. So this is C2 free producted with C3. So we've got our generator and its inverse here for C2, and then our sort of odd cycle for C3. And you can check that from any point here to say some point there, there's a unique geodesic. And so sort of the main question regarding geodetic groups is there a characterization of them? And the conjecture is a group is geodetic if and only if it is plane. So this was conjectured by Shapiro in 1992. And there is a theorem of Papasoglu from 1993 that says, if a group is hyperbolic and geodetic, then it is virtually free. So this is nice because if we have these sort of thin triangles, then we actually know, and we're geodetic, then we actually get ourselves into this smaller class of groups. And so the problems that remain are there geodetic groups that are not hyperbolic? And my feeling is that is possible. And the other problem is, are there virtually free geodetic groups that are not plane? And if I was going to say anything, I would say no. The geodetic groups seem like they need to be plane from what I know. So the main result of this talk is a generalization of Papasoglu's result, but to k-geodetic. So let the Cayley graph GS be k-geodetic, then if G is hyperbolic, then we have a bound on the side lengths of non-degenerate geodesic triangles. And we also have that G is virtually free. And by non-degenerate, I just mean the sides are disjoint from each other. So they're not sort of like something like this or bubbling or something like this. So it's just disjoint sides. Okay, so the proof of I is actually quite straightforward. Since G is hyperbolic, we know the geodesic triangles are epsilon thin. And then our unbounded side length, if we assume that there is one, will contradict our ladder corollary. And so if, say, this side is unbounded, then
E-text.
What was that, sorry?
I don't think there was a question, it was just some background.
Okay, yeah, nice. So since we know that if we assume that this side is arbitrarily long, then one of these sort of halves are arbitrarily long, and then we would get an epsilon sort of close to sides, which would build us a geodesic ladder. And so that would contradict our ladder corollary. So that's nice, because what that tells us is there's actually a finite number of non-degenerate geodesic triangles, because we've got a finite generating set and there's a finite side length. So the proof of part 2 requires a characterization of virtually free. And the characterization that we use is a group is virtually free if there exists a finite set of words with respect to the generating set, with respect to some generating set of G, such that the words in that, with respect to that generating set is a geodesic if and only if W has no factor in F. So this F is a set of non-geodesic words. And so that's a result due to Gilman, Hermiller, Holt, and Rees from 2007. And the way that they show that is because there's another characterization of virtually free in terms of a push down in automata. Okay, so we're going to suppose that we have a nice geodesic word, and then we add an extra letter to it. So then we've got 3 options. Either the new word we get is a geodesic still, so the length has increased, or the length stays the geodesic from here to here is larger, or the geodesic from here to here is actually the same length. So it looks maybe something like that. And it's the same length as this geodesic, or it actually moves a step closer. So I've sort of demonstrated that in these 3D diagrams. And so we just need to come up with a finite set F with all these properties. So I plus the fact that S is a finite generating set implies there's a finite number of non-degenerate geodesic triangles. And we can let F be the set of words with non-degenerate triangles that appear in case B and C, as well as the words S and S inverse. So what I mean by that is we take the non-degenerate triangles, we take this word here and put it in F, assuming that the triangle looks like this and not something like, say something like this, because that's degenerate. And that will give us an F that's completely what we want. Any non-geodesic word will have a factor inside F, and that proves virtually free. So a conjecture we have is there's actually no difference between k-geodetic and geodetic. So a group is k-geodetic for some k greater than 1, if and only if it is geodetic. And so combining that with Shapiro's conjecture gives that a group is k-geodetic if and only if it is plane. And that's all for today, and thanks for listening.
Thanks for your talk, Kane. Does anyone have any questions? Well, if there are no questions, let's thank Kane again